In this tutorial, we'll bring crystal structures to life in Blender using geometry nodes and metaballs. Ultimately, we'll create a rig that mimics a living, breathing electron density map. In part 1, we'll prepare our models in PyMOL, then we'll use a Python script to import the atoms into Blender as a point cloud. And finally, we'll instance spheres on each point using geometry nodes. We're going to kick things off in PyMOL, which is more or less the industry standard for making figures for publication. And it's a very powerful image generating tool, and it's powerful for another reason, and that is that it's directly linked to the database, the RCSB database that houses all of these structural coordinates. So if we want to load a model into PyMOL, we simply write in fetch and then an accession code. In this case, it is an accession code that I've pre-selected for this tutorial. And bam, we have our whole model, or the whole structure, is now contained in our window. And we don't need all of these copies and all these molecules that are going on, so I'm going to isolate a single chain. I'm just going to call it structure, and I'm going to isolate chain A. And then if we turn off all other views, this is a little bit simpler. This is the model that we will be dealing with. And what you're seeing by default, this is called cartoon view. You have your alpha helices, as these helices here. You have your beta sheets, and then you have your loops, which is everything else in between. And what PyMOL is doing is it is reading the structural file, which is really just a text file. That's a list of every atom in the structure, and then certain information such as the atomic identity and the X, Y, and Z, or the spatial coordinates of each atom. And it reads that in, and then depending on what your selection is in terms of representation, it calculates and layers geometry on top of that. And aside from cartoon representation, you've probably seen surface, and something that is going to be very similar to what our model is going to look like in its early stages would be spheres. And you can start to get an idea for how powerful PyMOL is for generating images. But that's really where it stops. And there's a really good reason for that. And it's that crystal structures are snapshots of molecules. And as such, they are not supposed to move. They're not meant to move. So there are very limited animation and movie making tools in PyMOL. Blender is much better suited for animating things, but there's a huge disconnect between what comes out of PyMOL and what goes into Blender. And that's what this workaround that I've developed is for. It's meant to get the atomic information into Blender in a way that allows you to guide your animation using the spatial coordinates and their identity. And I'll show you what I mean. So, for example, if we were to export this geometry, it would be a whole bunch of different spheres layered on top of each other. And it's confusing and it's messy. And even if you have a slightly better interpretation, or a much better interpretation like surface, as pretty as that looks, and you see these really cool channels through here and all that, what you're exporting is really just a water balloon. You're just exporting the skin of this model, nothing on the inside. And cartoon, while it is maybe the best known representation, it's a mess because it's not being exported as one discrete model. It's a whole bunch of different models pieced together, and I'll show you what that looks like. So we're going to do both, actually. We're going to export the raw geometry. I'll show you what that looks like. And then we're going to export a PDB file, and then import that into Blender using a script I developed and the other geometry node method. And what we'll do before we launch down that part of the tutorial is I want to come in here and I want to turn on hydrogens, because if we're talking about making an electron density map or a mock electron density map later, the hydrogens really give it a really cool visual feature. So I'm going to add these in because they're not on by default, and you can't see them in the cartoon view, but they'll be there in the model later. The other thing that we want to do before we export anything, especially if you're exporting multiple models and you want any hope of them lining up in Blender later, is we have to reset the camera. And that's because PyMOL has some relationship between the camera and what the coordinates are of what it exports. So if you export in one position and then move and export in another, by the time you bring that into Blender, all the geometry will be in whatever position it was in when you told PyMOL to export. But that's an easy enough fix. We're going to go up here to reset, and you see it snaps right back to the default view when we came in. So after we get the model looking pretty, in this case I'm going to use just the default cartoon representation. I'm going to go up here to File, Export Image As, and VRML. And when I save that on my desktop, I'm going to call that structure cartoon. And now with the same model, everything else selected, we've turned hydrogens on. I'm going to go, instead of export image, I'm going to export molecule. And you can select everything that's enabled or an individual layer, which is what I'm going to do. Click Save, and by default it wants you to use this PDBX format, but I've at least written the script and tested it only with this PDB format. I'm going to save this as structure, and away we go. We are done with PyMOL. We can open a new Blender file, and that's what I have here, except for adding some reference images I'll be showing you momentarily. We can delete the default cube, and we can import the cartoon structure. This is the direct geometry output from PyMOL by going to File, Import, and X3D Extensible 3D. Navigate back to that file, give it a moment to hang and load everything. And what we'll get when it's done is our geometry, as you can see here. And also, confusingly, a new camera that I don't enjoy and a direct light that I also don't enjoy. We can rename this cartoon. And this looks pretty close to what we saw in PyMOL. We have the helices, we have the beta sheets, we have the loops, but it's got this weird pattern to it. And even if you go right-click and go on Shade Smooth, it's still hanging out there. And that is because if we go into Edit mode, it's a whole bunch of different objects that are joined together. And there's vertices on top of each other and a lot of things that are making it difficult to interpret. There's a quick fix to this is with everything selected, you can click or type M to merge by distance. As you can see, we got rid of 154,000 vertices. And that makes things a bit easier. Now if we click on Shade Smooth, we have something that even more closely resembles what we saw in PyMOL. But you'll notice there's not an atom to be seen anywhere. We are now strictly dealing with the geometry, which is already an interpretation of the atoms, of the atomic coordinates. And you can animate this, but it becomes really hard to do that because you have no reference anymore. And as hard as it already is going to be in a program that's not designed for crystal structures, it's even harder dealing with just geometry. So that's why I devised this alternative method. And it all starts with a script. And this script is called ImportPDBCloud.py, and it will be available on GitHub at the link below. And I'll run this and explain what it's doing while it runs because it does take a moment. I'll select my structure, PDB, that I exported. That's the molecule export, and click Import. And what it's doing is it's reading through the PDB file that PyMOL spit out, and it's looking at every line and saying, oh, there's an atom. It's reading the atomic identity, and it's also reading the atomic coordinates. And then it's just creating a new point for each atom that's in the file, and that's what gives us our final point cloud. And along with importing the point cloud, it is also storing the identity of each atom type in its own vertex group. So if we want to look at, for example, or select all oxygens, it's now in this vertex group. You click on select, there are your oxygens. If you click on sulfurs, there are your sulfurs. And we're going to use these data later to give each atom type its own unique scale and give us a little more control over the display versus it just being spheres. And what I'd really like to do at the end stage of this is use the point cloud to make sort of an electron density map that overlays with some transparency over this cartoon model. And I mentioned orientation-wise, we have to fix this. We have to make, for example, this line up with its counterpart in the point cloud here. And there's a quick way to do that. One is you look at, or you select whatever the geometry is that came in, and we look at some of the properties. For some reason, Blender applies a rotation to the object when it comes in. So if we reset those to 0, you see that we're pretty darn close to where we'd hoped to be. And to get it, to help it limp into good enough territory, we just need to reset the origins to geometry. So I'll do it with the point cloud first, then I'll do it with the cartoon, and then when I shift click select the point cloud and parent without inverse, now it snaps. And that is pretty darn close. Now, if you are just planning on making a static image, or you're not planning on using an armature-based animation, you can skip this next step. But what will become apparent in the next stage of this tutorial is what I'm about to do, which is to take this structure here, this one point cloud, and I'm going to duplicate it. And I'm going to give this a name. I'm going to call it armature. And with both of these selected now, I'm going to rotate all of this into a view that I find a little more user-friendly. All right, that's pretty good. And then for the sake of clarity, we're going to put this armature in its own collection. And we will tuck it away for later. Now, with our structure selected, we can start layering on the geometry nodes. And to start that process, we'll go into Geometry Nodes. We'll click on New. And this is the basic representation of the data. We have over here the structure, and this is our point cloud with the X, Y, and Z positions of each atom. And now we want to tell Blender to put some shape on top of each of these points. And the way that we do that is simply using a node called instance on points. We're going to plug this in here, and you'll notice that everything disappears, which is going to happen a few times in this tutorial, don't worry. And that's because it has points, but there's no actual geometry. There's no instance. We're not telling it what to put at each of these points. That's easy enough to fix. We can just select, or we can just create a UV sphere. We'll zoom in a little bit and shade smooth to make it pretty. And then with our structure selected, let's pin this geometry node so it doesn't keep moving around. We'll drag in our sphere, and we'll plug that geometry in as the instance. And now we have something that looks like the sphere representation that PyMOL can spit out. Now, as we start considering individual scales for the different atom types, we need to take advantage of these vertex groups that the script created. And to do that, we look at our group input, and we go over to group, and we can let's add one new one to start, and we'll just call this H. And if we come over here into the modifiers tab, we see that there's this attribute toggle node. So if we're looking for a vertex group, it wants a float, but if we click on this value, or on this button here, now we can select our vertex group for hydrogen. And we have it selected here. If we drag this into this input for selection, you see things shifted a little bit. And that's because instead of showing every atom type, when we plug into selection, it's now only showing whatever that selection is. In this case, whatever's in the vertex group, whatever's in the hydrogen club, is what's being displayed here. And then if we adjust these scales, now we have the ability to adjust each atom type based on whatever vertex group it's in. So to take, or before we do that, I'm going to add in some more vertex group grabbing inputs. O and S. And this is as easy as clicking the attribute toggle, selecting your vertex group, and S. Now, to take advantage of this scale, we can use an input here that is a local scale, but I also want the ability to scale all the atoms relative to each other. So I want a local scale and a master scale. I'm going to factor them together using a math node. And you can play around with whatever value you like. I've had the, or whatever setting you like. I've had the best success with multiply. So we can add in a hydrogen scale. And eventually we can add in a master scale. But before I start plugging away, to keep myself organized, I'm going to add all the local scales first, and then I'm going to add the master scale. So that's carbon, nitrogen, oxygen, and sulfur. And last, I'm going to add a master scale. And I'm going to give all these a value of 1. Okay. Now we can take the local hydrogen scale and plug that in up here. And we can take the master scale and plug that in down here. And now what we've done is, by plugging all this in as part of the modifier input, we can adjust the hydrogen scale. Oh, would be helpful if we plug this in first. So we've got them both multiplied together. Plug this in here. Now we have this scale. So if we go back out to the modifier tab, we can scale here, and we can scale on the master scale also. All right, that's good news, but that's good news if you are a hydrogen. Less good news if you're into the other atom types that we have in the model. So we have to duplicate this setup here and then change the settings for each atom type. And that's easy enough. I'm going to make these into a group. I'll select both the math node and the instance on points, Control G. And this brings you into an interface that's very much like object mode versus edit mode. You can hit tab to toggle back and forth. And this is the group we've created. I'm going to call this H group. And if we go into H group, we can make our lives a little bit easier by giving these inputs some names. So I think points, instance, and selection are good enough. But for value, it would be nice to know that this is the local scale and that this guy is the master scale. Now if we back out of here, we have local scale, master scale, everything makes sense. So if we want to add, let's say, the carbons next, we can duplicate this group, plug in our inputs. We have our points. We have our geometry as the instance. Our selection is going to be the carbon. We've got a local scale, and we've got a master scale. And if we want to join this geometry together, there is a very helpful join geometry node that we can use. Plug that in there. And now we have our carbons added in. And we can illustrate what this looks like, of the sort of control we have, by scaling up just the carbons and scaling down the master. And now we have carbons and hydrogens at different scales. Make it even smaller. And what I'm going to do is first rename this to carbon scale so that we can differentiate between them. And I'm going to start to duplicate these and twirl them down to move them out of the way. creating different groups for the remaining atom types. I'm going to fast forward through that. Okay, so there's our whole node setup. We've got our geometry and our other inputs coming in. We've got our main object that we're using to replace everything. We're instancing on points for each type and joining that geometry together. Before we go any further, let's keep this clean as best we can. So we're going to select all these nodes that have to deal with building the model, and Control J to join them up as a frame, and then name this model. And we can go into layout mode and see what this network, this geometry node network has created for us. And it's really this ability to scale each of these individually that I was looking for. And it's all scalable right here. A word on scaling. So I looked up, that's where these reference images come in handy. I looked up some atomic radii, and you really just you can pick whatever you think looks the best. But basically, I picked the atomic radius based on covalently bound atoms. And this here is in picometers, but to keep myself from having to have a really gnarly or really tiny master scale, I normalized everything to 1. So if we select the point cloud again and start to enter these values, now we have something that is more or less reasonable, if not accurate. And everything is scaled accordingly. And if we want to adjust the master scale, there we go. All right, so that's looking pretty good. And I mentioned at the top that we are going to be using metaballs eventually to replace these spheres with. I don't recommend doing it yet, because metaballs basically can create one continuous membrane around all these points, and it's very computationally intensive. And aside from being other difficulties with getting geometry nodes to accept metaballs, it can be really just intense for your computer and a little difficult to deal with. So through the animation and shading process, I recommend keeping it as spheres, or you can switch this out for any other type of geometry you want. And it's pretty straightforward in how to do that. So we imported a sphere before, but let's say we wanted to replace this with Suzanne. We can simply drag in Suzanne and then use this geometry to replace the instances that we're using currently with the sphere. And if we zoom in on this, we can see an army of angry monkeys staring back at us. So it's really whatever you want to put on these points, you can. But because I find Suzanne unsettling, in this instance, I'm going to remove her and instead take advantage of something we can do now that we won't be able to do later when we have metaballs, is assign a different material to each atom type. And that is pretty straightforward. It's just a matter of inserting a set material node right here. And I'm going to speed this up and create 5 different colors, one to assign to each of these groups, so that we can visualize things a little better. And I do find it helps with the wiggle animation visual read as you're doing it, and also with the armature animation. All right, so now we have those colors together, and it's a simple matter of, with this set material node in place, inserting whatever color we want our hydrogens to be in this instance. And we can duplicate this node and add this for orange. It can be green, blue, and purple. And if we look at this in our layout window, Now we have something that's starting to look a little more biologically accurate. So in summation for this part, we have our point cloud brought in to represent where the individual atoms are. We have layered on top of that spheres and given each atom type a unique scale that allows us a level of control that you just don't get if you export the raw geometry out of PyMOL. Thank you for watching, and stay tuned for part 2, rigging.